Okay, in this video we're going to be talking about reactions called direct alkylations. In other words, how can we add an alkyl group directly onto a ketone, an ester, or a nitrile? This doesn't work very well for aldehydes. I don't want to get too much into that, but you'll find it mainly works with ketones, esters, and nitriles. Now, given that the types of reactions that we have been discussing, the malonic ester synthesis, the acetoacetic ester synthesis, one thing that we need to understand that all these three have in common, well, let's see, can you guys figure out what is it that all these three have in common? And I'll give you guys a clue. This has 6 of them, this has 3 of them, and this has 2 of them. Well, the that I'm referring to are alpha hydrogens. 6 here, 3 here, 2 here. So in theory, if we use a strong enough base to remove one of these alpha hydrogens, this one, or maybe this one, or maybe this one, we should be able to alkylate the enolate with some sort of alkyl group, with a leaving group on it. And that's actually quite easy to do. The only thing that's different here is we talked about previously doing something along these lines. I won't go into the malonic ester synthesis here, but we talked about removing these 2 alpha hydrogens here. We also said these were particularly acidic because they're between 2 carbonyl groups. Now, you've also seen before that, for example, these 2 are more acidic than these. These 2 hydrogens are more acidic than the hydrogens on each end of the molecule. So that means, hopefully you can understand, we need a stronger base to remove these hydrogens than we do to remove these hydrogens. Now, we use ethoxide for these. That will not work for other hydrogens like these. We have to use a stronger base. Now, we've talked about this a little bit in class, so I will bring it up right now. We use a much stronger base called LDA, lithium diisopropyl amide. I mentioned in class it's kind of a misnomer because it's not really an amide at all. Crap, bloody things are joining together again. It's not really an amide. If anything, it's the conjugate base of an amine with a lithium plus here. The isopropyl groups make this a crappy nucleophile and a very strong base. So what this means is this can deprotonate any alpha hydrogen like this one, or this one. And if you have the enolate, then you simply just add in whatever alkylating agent and you have your direct alkylation. So let's take a look at an example. All right, if we were to take acetone here and we react it with LDA, let's call that step 1. The book talks about THF, that's just a solvent. We're not going to be doing this in labs, so I'm not really that bothered about it. The important species is LDA. The idea is LDA generates the enolate, and then let's say we add in some very strong alkylating agent. And this is one of the strongest known if you want to add in one alkyl group, methyl iodide or iodomethane. The iodine is such a good leaving group, this methyl is very electrophilic, and the nucleophilic attack will happen very easily. So what we end up with is something that looks like this, where you have a methyl group that's alkylated at the alpha carbon, essentially this. That's the product. And in each of these 3 cases, you'll always alkylate at exactly the same place. You'd alkylate here, you would alkylate here. Alright, now let's take a look at the mechanism. It's very, very similar. Well, it isn't very similar, it's almost exactly the same. If we were just to use an ester here, alright, and let's just draw out this, and we want to do a alkylation at this carbon, or this hydrogen I should say, because that's the only acidic hydrogen now. Alright, here is our LDA, and we know from what we've seen before, the base grabs that hydrogen, kicks the electrons from the carbon-hydrogen bond into the carbon-carbon bond, forming a double bond, and what we end up with is the enolate, the structure that we've seen ad nauseum now. You've seen it a whole bunch of times. This is our enolate right here, okay? Existing in two resonance structures, one with the oxygen here, one with the oxygen on the carbon. And then, after we've done that, at that point, this was essentially step one so far. Then in the second step, we just take the methyl iodide, or whatever alkylating agent we're using, and we just do exactly what we did before. The O- from the enolate that you've seen before, written in exactly the same way, reforms the carbonyl group. That sends the nucleophilic electrons down to the electrophilic atom, in this case carbon, and kicks out the leaving group. Again, in exactly the same way you have seen before. So we end up reforming our carbonyl. In fact, we've essentially reformed our ester. That's what the ester that we had before, and all we've done now is added the methyl group. So we've gone from methyl ethanoate or methyl acetate to methyl propanoate. And that essentially is direct alkylation. All right. If you were to think about how does this happen with a nitrile, I'm not going to go into the mechanism because it's exactly the same as what we saw. But again, we can say this is a two-step process. The first step is, go ahead, you guys, shout it out. It's exactly the same as was on the last slide. I suppose this is, Andy, you're right, I suppose this is kind of like chemical Sesame Street. Shout out the answer. And I'll tell you you're wrong, dumbass. No, anyway, I'm sure you guys are right. I'm sure everybody got LDA there. To deprotonate the alpha carbon. And then, let's say we add in our iodomethane, methyl iodide, whatever you want to call it. Gives us the same nitrile, but that is now alkylated. Does that make sense? I hope so. So, let's see then if we can use this reaction to make this product. I'm just going to draw a product out, and I'm going to ask you guys, this is the kind of question that's given in the book, can you use an alkylation reaction to make a product such as this? Now, it doesn't tell you what to start from, but the key here should be, if the question's saying, can I use a direct alkylation to make this product, then I've got to be looking for one thing mainly. Where is my alpha carbon? And what alkyl group is coming off my alpha carbon? Well, you guys can see that this is the alpha carbon. And so therefore, the group coming off the alpha carbon is this one. In other words, that's the group that must have been added in via an alkylation. So my starting material is going to, in this case, is going to be this, but without the alkyl group. So let's just draw that out. So whenever a question is asking for something like this, unless it's asking for a total synthesis, which in most cases it won't be, it'll be asking for how do we go from something like this to something like this. And it's a very simple question with an equally simple answer. It's two steps because this is a direct alkylation. The first step is the species you use to remove the acidic alpha hydrogen, and that's our lithium diisopropylamide, our LDA. And the second step, is it methyl iodide in this case? Well, hopefully you'll say the answer is no, because you're adding in two carbons. So I could say something like this. I could say ethyl iodide. It turns out the iodoalkanes work the best. It doesn't have to be that though. You could say do something like this. Either one of these two would work just fine. Alright? Potentially even this. We aren't going to get super picky about it. The point is each one of those adds in two carbons, and that is alkylation, direct alkylation. Alright?